Hi everybody, thank you all for being here. My name is Abdullah Al-Hamdan. I would like to start to say welcome to the Jurassic Park. But unfortunately here we will not discuss about the movie, we will discuss about the security risks about Deno and its ecosystem. But first of all, what is Deno? Deno is an emerging JavaScript runtime with a focus on security in mind. It uses Rust as a memory-safe language to implement the APIs surrounding the JavaScript engine. It also has the permission system that intercepts the interaction between these system calls and the operating system side with the APIs, sensitive APIs in the runtime itself. And also, Deno supports import third-party libraries using arbitrary URLs, and this could give the definition of decentralized software supply chain. So, Deno might look like the wizard that solves all the problems and miseries in Node.js and NPM. So our motivation for this paper is to study the security risks of Deno, and then we evaluate how these features influence the security in general. With a little bit of a spoiler, the Deno runtime has for sure a smaller attack surface in compared to Node.js. But unfortunately, some attacks could be mitigated better in a proper way. But also, there are new classes of attacks or threats to JavaScript and TypeScript applications because of the new some of the new features in Deno. So to dig deeper in the details of our results, we divided our paper into three aspects to study. The first aspect is basically we study the security and the attack surface of Deno in general, and we examine the permission system of Deno, and also we evaluate the software supply chain of Deno. So moving to the first aspect of our study, we evaluate the Deno security model and the attack surface. So we say we need to answer the question of how these features helped Deno to mitigate some attacks. So first of all, the security features of Deno starts with it is resistant to memory attacks since it uses the Rust language. And also learning from NPM mistakes, it uses distributed supply chain. As an optional feature on top of the distributed supply chain, it has the third-party source code integrity checks. So this could help Deno to keep the integrity of the third parties of source code that used for Deno. And also it has the permission system that intercepts the communication or calling these sensitive APIs. To examine those features, we studied the 12 years of papers from the time of the study to 12 years before that, the papers related to Node.js, NPM, and related things to the risks on that regard, and we came across some results. So I first of all would like to invite you and encourage you to read the paper to look at more details and more attacks. So one of the attacks is the most popular attack for Node.js is the prototype pollution. So the prototype pollution starts with that you are trying to tamper the objects through a prototype chain into other objects. So let's start to discuss like an example here. So you define an object and then you try to use proto __proto to try to access the prototype chain. But what happened to Deno? Deno were able to block this attack since it freezes these properties. So, is it only __proto the only way to do prototype pollution? Let's see. So the first line here that we have to define the same user, we changed the __proto to constructor.prototype. We define another user, and then we try to see, and oops, we got this prototype chain pollution. So we can say that Deno is basically partially affected, but not yet mitigated. Other type of attacks where Deno were able to change or to move the risks from being runtime centric to a end user centric. So one of them is basically the command injection. Command injection allows the attackers to run arbitrary code commands on the application. So looking and considering this code, basically you have this prompt message, and then you have naive eval to the user input. So the permission system of Deno is basically do the permission checks on the runtime by default. So if we run this code and we consider this attack where it tries to read etc password, the permission system will check these system calls and then give a prompt up message to the user where it's his own choice to allow it or not. But what if we define these permissions in advance? What would happen? So we give the same attack to this, and unfortunately, now the permission system is no use, therefore the command injection is still possible. So evaluating the attack surface of Deno, we came to a result that it's for sure have a less attack surface, but still there are a set of attacks that could be mitigated in a proper way, and we communicated to the authors of Deno to solve some issues. So the second aspect of our study is basically to study the permission systems of Deno. The main goal is to see how robust is this permission system. So the permission system of Deno, it's a runtime permission system that intercepts all the calls to critical functionalities, and these permissions cannot be granted by anything but by the user. So let's assume an example here with a Deno application that has these two instructions. The first instruction is to read a file, so it calls a system call, and then this fetch URL that requires a network operation. So the V8 engine forwards these instructions via permission checks to the Deno runtime, and Deno runtime forwards these requests to the user whether to accept or deny. So if the user accepts these permissions, Deno runtime forwards these things to the system calls, therefore the operation will continue. Otherwise, the permission system will terminate the execution and the code will terminate. So to evaluate these things, how we evaluate the permission system of Deno, we try to escape the permission checks of Deno. So one of the two examples that we got CVEs for them is basically that we are trying to escape the permission system using static import. So this attack basically starts with 2 rounds of building this attack. The first round is basically we prepare the attack. The second round is to run it. So how to prepare the attack is basically, first of all, we get the path name for the currently running code, and then we read the content of the running code, and then we read other files that we wanted to leak their information, and then we built our own attack. Let's assume that we are trying to make a request to attacker.com holding the content of etc password. And then we write the same content of the attack that we want to the same file that we already read. So as we can see here, the permissions required for this attack is only read and write the file, nothing else. So on the second run of the attack, as we can see here, for the same file, we see this line of code is appended or pre-appended to the source code. As we can see here, there's an import statement that tries to call something in the attacker.com where this attacker has a sniffer to read or parse the requests. So as you can see here as well, we find that the content of the etc password is also appended to the URL. So looking at the same permissions we have, we do not have any network permission while we run this attack. But this leads to a data exfiltration through static import. We assigned to our finding a CVE for that. The third aspect for our study is to study the security and evaluate the security of the Deno software supply chain. So Deno software supply chain, learning from the Node.js and NPM mistakes, is basically allows to import third-party source code packages from any available domain through any valid URL. It also, deno.land, has, which is the main contributor to the distributed supply chain for Deno, has this package version immutability. So what does it mean? It means that whenever you have a publisher publishes a package version, no one can delete it, no one can change it, no one can alter it, even the author of that package. And also it allows importing individual files instead of importing the whole package. So in theory, you can say that the import tree is getting smaller and smaller. This is in theory, but we didn't prove it yet. So to evaluate the distributed software supply chain of Deno, we did an empirical study. So at that time, we collected all the packages at deno.land. There were like 5,400 packages. And we extracted all the transitive and the direct URLs, resulted into 10,500 URLs, and they were like distributed into different 21 domains. One of the things that we studied regarding to Deno distributed software supply chain is to see the impact of unavailable URLs to the software supply chain. So one of the things that we found across our study of time, the median of unavailable links, they were like 220 links. One example is on the 23rd of September, there were like 283 unavailable URL. Almost 60% of these URLs, they were available at the day before. The amplification factor is a bit high, where we can see 1,332 affected transitive dependencies. And we can see also on the 5th of March, there were like 276 unavailable URLs affected 1,015 transitive dependencies. And at that time, one of the main contributors to the Deno ecosystem is Deno package. 4 of them, they were like having a huge amplification factor, a significant amplification factor with 10% of total affected packages. So in our takeaways ends up with the Deno that it's an emerging JavaScript runtime with a focus on security, but it still has these challenges. And also Deno for sure has a smaller attack surface, but many attacks could be mitigated in a proper way, better way. Maybe they have to investigate more about it. And also, Deno permission system is one of the success stories to minimize the risks of the supply chain. But still, these permission systems has problems within themselves. And in the end, implementing a decentralized software supply chain is quite challenging, especially when we talk about server side. So therefore, we recommend the people who contribute to that to have a uniform package distribution policy. Thank you all, and I'm happy to receive your questions.
Thanks. Time for one question. Okay, I have one. So you showed many attacks. In the paper, is there any idea to mitigate them or not yet?
So we gave a rough pieces of advice to the people of Deno to mitigate these attacks, but we didn't evaluate them. So these mitigations are basically rely on existed research to say that, for example, to avoid, for example, the package distribution policy, we inspired it from other research available before to solve this problem in decentralized software supply chain, for example. Yeah.
Okay.
Yeah.
Thanks the speaker again.
Thank you.